Hi, I'm Ryan Nickel, CTO at DSA Ocean, and today I want to talk about how to evaluate how effective hull appendages are in slowing down ship motion. Now there's three ways to do this, and we're going to use the generic fishing vessel as an example. So it's a pretty small vessel, and of course it's got a nice set of bilge keels there. When you're looking at the ship model particulars under bilge keels, you can see that the span is ½ meter. When you're designing a ship, though, you might want to find a way to gauge, how much chord should we use? Should we use more chord? Should we use less chord? What impact does that have on roll motion? And there's three ways that you can evaluate what happens to the ship and get feedback on how the design is affecting it. So the first thing is all in the RAO calculation, and this is most effectively done in the SeaKeep regular application. So the first thing you want to do is when you're doing the calculation, make sure you have this checkbox indicated here, has output roll damping. That's going to give you some useful information. So we'll run this. And what I want you to do is go to view output, and we're going to look at that roll damping feedback. So this is the first way you get some feedback. It's going to calculate this for every single loading condition, so different relative wave headings and forward speed. So maybe what we'll do is look at the pure beam case here at 0 speed. I'm looking for the C direction here, 75. Here we are, C direction 90 degrees. So it's calculating the roll motions. It really is the RAO because it's all in regular waves, and we go down here a little bit. We have the rudder deflections, and then here's the roll damping for that configuration for C direction 90 degrees. And what's interesting about this is that for the different wave frequencies, and then we have a resulting roll motion, then it's giving you a breakdown of the roll damping components. So here we have the total roll damping. Now this is normalized by the critical roll damping for the vessel, so you can see how much that is. And then it gives you a breakdown of where are those roll damping contributions coming from? Hull radiation, hull viscous, so this is going to be largely driven by that eddy roll drag coefficient, any maneuvering coefficients that are applied, and viscous, and this is going to be largely driven by the, of course, by the hull appendages here. This is really giving you an idea of what's happening from the bilge keels, and of course that's going to change with frequency. You see much bigger contributions in that sort of in this range here, and of course variations in the added mass is it's totally going to be dependent on the hull shape and so on and so forth. So it's one way of kind of quantifying what's really going on with that specific configuration. The other thing that you can do really quickly is in SeaKeep regular, just plot the actual RAO and take a look at it. So of course we're looking at 0 forward speed and head waves. You're not going to see any roll motion. Of course bilge keels are going to have the biggest influence on roll, but you can see here we've got a peak RAO value, and of course the peak RAO with the biggest roll motion, that's going to be the most sensitive to changing things like the hull appendages. So that's the second thing that you can do, look at the peak RAO and just see how that's changing. And there's ways of rapidly doing sensitivity studies to see how that changes, but that's another video. Finally, the last thing is checking what happens in a more specific sea state. So the RAO is all good, but it's not necessarily indicative of performance in what might be a much more interesting sea state. So with a spread wave pattern and an irregular sea state, we're just going to quickly run this case with the same ship, and it's kind of analogous to looking at what happens in regular waves, but it's just nice to look at the RMS motion. So at 0 speed, I mean, you can look at forward speed, you can look at all the different conditions that you want, but just at 0 speed and beam conditions, you can kind of characterize, well, we've got this much roll motion. Okay, so now if we go back and make a change to the bilge keels, and then go back and evaluate how much viscous force is going up, you'll start to see trends where we doubled the bilge keel size, but it's not really making an impact on, not really significantly changing things anymore, and you can kind of get a sense of how much value there is to adding certain kinds of hull appendages and their performance. So really I wanted to highlight just those three ways of evaluating the motion control performance, particularly from appendages. And thanks for watching.